Okay, so today we will continue. So yesterday there were a lot of essentially preliminaries, none of which involved category O, but it involved very important. The category O is a category of modules. So yesterday's lecture involved us discuss some important objects in category O, namely Verma modules and highest weight modules. So these are essentially the building blocks of category O. So we will start by discussing, reminding ourselves of just the definition to write down and then getting moving. Okay, so maybe this pen will work. Okay, so yeah, so this section is literally just a recap. So let's see. Okay, actually a couple of corrections first of all. So this thing that I mentioned. So two things about edit. You can update the lecture. That's what one thing I mentioned was you can look at monomials like this, fk, hj, ek prime, and where so you write down beta 1, beta n are the positive roots. I mean, you enumerate them in some way if you want, and then you say that it doesn't matter which way, and then I write down fk equals f beta 1 power k1, f beta n power kn, and then I said that ek should be in the reverse order, but no, I do want. This was fine. The correction is here. ek prime should be e beta 1 to the k1, sorry, to the k prime 1, e beta n to the k prime. And that's basically because if you want to take a lowering operator past others, then you have to write them in this order. Then this goes past all of them. I remember that part after. So, yeah. That's it. So okay, so yeah, so this is so you need to reverse the interchange the orders. Don't ask me why. Yeah, I can't tell you right now. But anyway, fine. So this is what it is. That is one correction. In particular, and of course, as that this part remains the same. So ki beta I or kj beta j equals summation k prime j beta j goes from 1 to n. So just change the 1 and n, 1 here and n here, and reverse order. That's all. Just to take that. Okay, great. So I should point out that Shushma is taking some very nice notes, and so well, the first lecture of notes is already posted, but maybe we can change that and then post the notes today. Okay. And the other point is an observation that I was wondering if somebody would ask yesterday, but nobody did, which is the following: that when we define this Harishchandra projection map, right? The map from the center UG to UH. Okay. And the idea was we write down any Z as some summation of this thing. So C, K, J, K prime, these things, F to the K, H power J, F E to the K prime. With now with the corrected definition, if you want. And then we say that we take the projection map, sends this precisely to summation to the J. Now, of course, you can ask, does this really, so here we fixed a sort of ordering or some enumeration of the positive roots and similarly of the simple HIs, but the HIs commuted, so that was not a problem. But these guys, the positive roots of the lower negative root vectors don't commute. So potentially, if I write down a different ordering of this, I get different monomials. And the question is, does this map depend on that choice of ordering? And the answer is no, it doesn't, because this doesn't. So I wanted to give you an explicit sort of map yesterday, but let me give you a clean version, which is coordinate free today. And that's really how one defines the Harishchandra projection. It might also be how Bernstein, Gelfand, and Gelfand define it. I should check. Anyway, and so the other thing, so one thing is that the lecture notes are being put up every day. The second is that the problems discussed in the tutorials are being put up every day as well. And at the first, I think I sent Amit yesterday. If not, they will be put up today. At the end of that place, I mentioned a remark, which is what I'm writing This doesn't depend on the choice, on the ordering of 5 plus above. So this ordering here, that ordering. Because it can also, because this is actually defined, because PR can also be defined as follows. VR. Okay. So here is what we do. We remember the TBW theorem again. The whole thing is about this. So it says that the multiplication map U of n minus tensor UH tensor UN plus to UG is a vector space isomorphism. And we also know that UN, I mean, any Lie algebra, for example, any Lie algebra can be written as the scalars direct sum n minus times it. So times the Lie algebra ideal. There's a codimensional ideal, and you can write it this way, or you can also write it. Let me just, I'll say plus minus. Okay, so one way you can write it is this way, and another way you can write it is also UN plus minus times plus. Right? Basically, UG can be written as G times UG is the two-sided. G times UG is equal to UG times G. It's a two-sided augmentation ideal. So this is the same as this. Now, using these two properties, let me define the Harish-Chandra projection without any appeal to any basis or words. Now, so this implies that if you look at UG, by the PBW property and these things, so by these two properties, UG equals, consider this, n minus UG plus UG n plus. I'm not saying that these two subspaces are disjoint because, of course, n minus UG n plus, n minus times UG times n plus is a common intersection. But whatever this is, what is the complement of this? Direct sum something else. What is the complement of this? Can anybody answer? Okay, somebody has to answer. So let's look at it here. This is C plus n minus times un plus. So n minus times that part is gone. So only C is left here. Similarly, this is C plus un plus n plus. So n plus at the end. So again, un plus n plus part is gone. So only C is left. So you get C tensor UH tensor C, and that's exactly what remains. But multiplication of C tensor UH tensor C. So UG is this big thing and UH. So there's a natural complement, vector space complement to UH inside here. And now the projection map is simply the projection onto this point. Second component. Now it's not hard to show that because this guy is sort of, yeah, I guess this is a two-sided ideal. Because if you multiply by, so let me give this a name I. No, I can't call it I. I is the index set. Let me call it, GI. What should I call it? M. Let's call it M prime. So M is maximal, N prime is not maximal. Anyway, let's call it M. The claim is that M is two-sided ideal. So the claim is M is a two-sided ideal. Why is this true? Because UG times M well, okay, I think you can just verify. So UG times so M, so UG times this part of M just sits inside this part of M. So it's UG times N minus times UG, and then you have to check that sort of you take N minus to the other side, it doesn't die out. Oh, but maybe that's not quite correct. So if I take
maybe you should put this for G plus
okay, that it's actually we care about UG 0, but okay, from this you can say that maybe M intersection the center is fine, or M intersection UG 0 is fine. So the point is this is defined. Once you have this to be defined, you can directly check forget what M is, you can directly check that projections are. For all and that's because when you write Z as Z1 plus Z2 and Y as Y1 plus Y2, then Z1 times Y belongs to this, Z2 times Y, sorry. The other three terms will basically belong to this one. And only Z2 times Y2 will belong to this, so the projection is Z2. Okay, so that's the other correction. So now let's move. So as you see, now here there is no mention of any ordering of positive roots or anything. So this is why this actually goes. Okay, so now let's remind ourselves again of what we were looking at. We're looking at Verma modules and high-spec modules. And so, okay, so maybe 1A was this recap, and this was 1B. So now 1C. So Verma modules were, I'm not defining them again, M lambda, lambda n star. And then the quotients of these are the same as high-spec modules. So actually the highest-spec module is a module generated by one maximal vector. Right? But I claim that that is the same as quotients of other modules. And that's sort of the, maybe that this is sort of a universal property. Maybe, okay, maybe I should say this is if and only if this happens. And I said because of a universal property. Due to universal property. What is the universal property of a Verma module? Given a G module M and maximal vector M in M lambda. So now we know that M lambda stands for the weight space of lambda weight space of M. There exists a there's a G module map from the Verma module to M, sending M lambda to M. M lambda, remember, was the generator of M. I'm not defining again. So this is the universal property of Verma modules that any maximal vector, the moment you have such a vector in any module, there is a G module map from the Verma module, subjecting onto the submodule generated by that maximal vector. So what does this mean? Basically, why is this true? In some sense, let's write down the proof. Consider the map. G module map from M lambda to M, sending, sorry, so X times M lambda to X times M, right? For all X in UG. So remember that G module maps are the same as UG module maps. This is not associative algebra, but this is. And we know about maps of associative algebra modules. So X times and then lambda goes to X times. This is clearly a Verma module map. And sorry, consider the map. This is just the map. The claim is that this is a G module. Why is this true? Because the Verma module is given by one generator and some relations, right? So what is H minus lambda of H? Well, let me give this map a name. Right. So let's see. So phi of H minus lambda of H times M. Or maybe we want to just check the G module now. So let's just check it's acting by the generator. So phi of EI times m lambda is how much? By definition, this is EI times phi of m lambda, which is n. But because n was maximal, this is actually 0 for all. And this was also 0. Okay, no, fine. Sorry, I'm doing too much indirect stuff. Sorry. Let's do it from even more first principle, which is from the first homomorphism theorem. Take the map from UG. So UG itself is a left G module. So take it from the left G module to M. X goes to X times M. The claim is this is a G module map. X of course is X times 1. So why? Because this is the G module map is clear. I don't know what to say. There is nothing to check. So this is claim 1. But claim 2, moreover, what happens to EI? Phi of EI is EI times M, which is 0 for all I. And phi of H is what? It is H times M. And H times M is lambda of H times M, because M is given to be M lambda for all H in H. And what does that mean? It means that there is some kernel of this map. So phi of UG, summation UG EI plus summation UG HI minus lambda of HI equals 0. And now we are done, right? So that means that phi factors. So phi is a map from UG to M, and this gives this ideal. Let's call this I lambda. So phi factors from UG mod I lambda to M, and this is exactly the one. And sort of now, I mean, it's also not hard to see that now that highest weight modules, which are exactly submodules generated by such a vector, are exactly the same as quotients of Verma module because it surjects onto this. Okay. That's Verma modules, highest weight modules, and the universal property. And we saw, fine, we saw a few other things. So, okay. All highest weight modules, okay, fine. So that was one. So from last time again, so recall all highest weight modules. This is highest weight modules are H semi-simple with finite dimensional weight spaces. Maybe I'll give it, let's call it V. So, what do I mean? I mean that therefore, i.e., V is the direct sum of mu in H star V, and all dimension of the mu is finite for all. But now, can I improve on this H star? A priori, mu can be any weight in the dual of the Cartan algebra. But because this is a quotient of the Verma module, remember that the weights of the Verma module themselves, how do we get them? You can write the Verma module this way, but also remember that the Verma module was I'll put it here, as n lambda is the same as un minus applied to n lambda. We saw that last time. And so is the same for V. V is un minus applied to m lambda. Let me call it m lambda. This is the image of m lambda, the generator in the quotient. And so what does it mean? It means that the weights of this guy are not just contained in H star, I can improve on this guy to say it's contained in lambda and then subtract a bunch of positive roots because you're applying negative root operators to it. So it's basically lambda minus z plus times the simple or times the positive. Okay, so that's the extra stuff. And now what we said last time was continuing the recall part. Maybe I should call this 2. And then this is A and this is B. Another recall. Another recall is simply that if V is something like this, so if you take a quotient of highest rate module, then it's a quotient of a quotient of a Varma module. So it's still a quotient of Varma module. So that's just another highest rate module. But I can take a submodule of such a module, or submodules of V of such a highest rate module V are also at semi-simple. With finite dimensional wave spaces. The fact that they're at semi-simple was the last problem, the third problem, second one of the problems in the tutorial yesterday. And because they're at semi-simple and contained inside here, these dimensions are finite. So in the submodule, the dimensions are even smaller. So they are also finite. Okay, so that was also said yesterday.
Yeah, sorry, sir. Hello.
Yeah, go ahead.
So you are considering this EM, this in the this proof of this part C. This is small m. You are considering of weight lambda, right?
Where is M? M is in M. Yes.
Okay, but what is the guarantee that this EM will such EM will exist? I mean, in this capital M is a G model, right?
That is the universal property. You are given some data and then there something nice happens. That's what we are given.
Okay.
Okay, so now let me write down some properties of highest rate module. Okay, so here is what these satisfy. So maybe satisfies 3 properties. Let me write down these properties. V is singly generated. Right? V is exactly equal to UG times m bar lambda or UN minus times m bar lambda. V is H semi-simple with finite dimensional weight spaces, but okay. And the third is this is the fact that we are going to prove, and this is a proposition. N plus acts locally finitely on V. I have not defined what this means, so let me do so now. And so N plus acts locally finitely on V. Okay, so let's see what this means is that is for all V in this highest rate module, if I start applying the raising operators, the EIs, again and again and again, N plus EI square, EI times EJ, I apply all kinds of operators. I have to speak, and starting from one vector, I go up. I stay only in one finite dimension. I stay in the finite dimensional subspace. That is the claim. Okay. So I'll draw a picture also and so on. But so first of all, what does it mean to apply EI? All kinds of EIs. It basically means I'm applying all sorts of words in the EIs, and therefore I'm just really applying the universal enveloping argument. If I look at UN minus times V, UN plus times V. Now, first of all, capital V is a G module. So of course, this is contained inside capital V. That part is right. The point is the dimension of this subspace of V is finite. for every starting point. That is the definition of locally finite. So let us prove this. But before proving it, let's see an example. I mean, example meaning let me draw a picture. So let's say basically this is going to explain how the proof goes. So it's really proof by picture. Right? So I have some, let's say G is SL3. And did anybody draw pictures of root systems for you in your previous? Yes, good. Therefore, I will draw the picture of SL3. So alpha and beta. And then this is alpha plus beta and then the negative. I just care about alpha and beta. So let's see. These are the two simple roots. It's enough to work with them. Right? So now let me write down m lambda. So let's say, suppose lambda is somewhere here. Now, let me go inside. Okay. I have m lambda. Then I have lambda minus alpha 1, lambda minus alpha, lambda minus 2 alpha, and dot dot. Lambda minus beta, lambda minus twice beta, and dot dot. This is lambda minus alpha minus beta, lambda minus twice alpha minus beta, and so on. Okay, fine. Maybe I'll take, this is a good one. So now, okay, we said for all V in V. So first of all, so I'm going to actually, well, one can do even better. I can prove that, so you know what n plus direct sum h is called? Anybody? N plus direct sum h. The Cartan sum.
Borel.
This is the Borel Saval. So if I take a bigger Lie algebra here and this is finite dimensional, then if I take a smaller Lie algebra, it's also finite. The claim is in fact U of V plus the Borel, as V is finite dimensional. Now, why am I considering the Borel? Because of what we did yesterday. Suppose you have V, and V is not necessarily a weight vector in the weight space. V is a combination of vectors. Then using the Borel algebra, using the powers of H's, I can, and then some interpolation polynomials or some sums and differences of these powers, I can separate V into individual weight vectors. And if each of them, now to each of those weight vectors, I can apply UN plus and get finite dimension, then for V being all of them, I can get finite dimension. So I'll say that more precisely below, but the idea is let's maybe start from this vector. Let's say I have a weight vector over here. Suppose my V is belonging to this. Okay. Now I apply all possible raising operators. Where all can the weights of such raised operators go? This is lambda minus 2 alpha minus beta. So basically, what all, if I apply some raising operator, something EI or EJ or something, to a vector in this weight space, what are all possible weight spaces where that vector can go? So you have to remember the basic fact that if you take UG, no, by now they should know this. UG times, let's say UG times beta, and then you take any module and you take M lambda, let's say M mu. This is contained in what weight space of M?
Mu plus beta.
Mu plus beta, right? So now I'm only adding positive roots because I'm applying n plus and powers of n. So beta is going to be a sum of positive roots. My m or my v is in v. Yeah. So what are all the possible roots? So this is lambda minus 2 alpha minus beta. Okay, alpha and beta being the simple roots in SL3. So what are all the possible weight spaces where this where some raising operators applied to this weight vector V can then So basically, you have to keep adding alphas and betas to this vector. So you can basically, this has to be less than whatever you lambda pick. So what are all the possible ones? You can add a beta, then you would get to lambda minus 2 alpha. You can further add alpha, you can get to lambda minus alpha, and you can get to lambda by another alpha. Or you could have added an alpha directly, and you could get to here. Lambda minus alpha minus beta. You could add another alpha, and you can come here. So these 6 places, basically you have to go, this Verma module is pointing downwards, but when you add positive roots, you have to point upwards. You have to only go above, and you're intersecting with something going below. And that's only going to give you a bounded area, bounded volume in general, in this case, bounded area. They're only finite, and because these are discrete points in the lattice inside a bounded area, bounded intersect discrete is finite. You know. So, therefore, there are only finitely many possible weight spaces above any weight inside the Verma module. When you go above, meaning when you add positive. And that is the key to the whole problem, whole proposition. Let me write this down. So, so look at two things. Therefore. So when I apply, so first of all, let's assume my V was a weight vector. That means when I apply these monomials, I will only land up with finitely many possible weight spaces. But that's not enough. The second point is that every one of these weight spaces has finite dimension. And so the number of weight spaces is finite. Each of them has finite dimension. I take the direct sum of all the eigenspaces, all these weight spaces. That is a finite dimensional weight space, and that's where the finiteness comes from. So the second part that I mentioned, so let's now write down the proof, and I will ask you that second part. Again. Okay, so proof in general. Now proof, not proof but picture. So say V equals V mu1 plus V mu n, V mu k, as I put in the tutorial answer sheet or whatever, tutorial sheet. So V equals V mu1 plus V mu2 plus V mu k, mu i's are discrete. Mu j's are discrete. Okay, so V is in the highest rate point. Each mu I, each mu j, sorry, so I should of course mention with which Vj belongs to V mu j minus 0. So I want some non-zero decomposition. Okay, so obviously if V is equal to 0, then the dimension of this times 0 is just 0. I'm not mentioning that, so say V. Okay, this is true for us. That means you can write down in terms of all the distinct weights that it has components in. So it's enough to show that the dimension of un plus times V mu j, let's say V mu j, is less than infinity for all. Right? Because if this is less than infinity, then when you sum up these subspaces, that dimension is at most the sum of these dimensions, and that's fine. And the sum of these subspaces is un plus a yeah, that's right. I will leave it. This is linear algebra. So I'll leave it to you. I won't spell out everything. Enough to show that this is true. So now I may as well assume that this is so. I.e. that for all mu belongs to weights of V, for all V in V mu, this is finite. But now let us write down mu. Remember that. So mu is in weights of V, which is contained. V is a quotient of the Verma module. So mu is contained in the weights of lambda, and this was lambda minus some or sum of positive roots. Right? Which means that mu can be written as lambda minus something. So mu equals lambda minus summation I belongs to I, ni alpha I, or sum ni non-negative integer. Maybe there is nothing to subtract, but whatever, you subtract 0. So now the claim is then you have, so now the claim I should say. Maybe I will call this, let's call this relation star. Okay, so using star, one checks that UG, so UN plus, not UG, times this vector V is contained in the direct sum of what? Of some weight spaces here, where you don't know it. Okay, so let me really say this. So that I'll call this as V. This was called mu, so let me call it mu belongs to S V mu. So all weight spaces where I have to describe the set S that we run over. So what are all possible weights here? So of course, whatever you do, this is the weight of V. So it's going to be V is going to be some weight less than lambda. S is lambda minus, and then it's going to be some combination mi alpha I. What are the restrictions on mi? That is the question. Right? Because every weight of the highest weight module is the weight of the Varma module, and so it is lambda minus some positive sum of roots, which is lambda minus positive sum of simple roots. So I can write it in this way. What are the bounds of the mi's? Because remember, this weight has to be above this weight of weight. So the weights possible have to be above the weight of mu because of this, and they have to be below the weight of lambda because of this. So these are all the weights between mu and lambda. All I'm asking is how does one write them down?
So each mi should be between 0 and ni.
That's right. Like that, right? So each mi has to be between 0 and 9. There are finitely many indices. There are finitely many values. So S is a finite set. That is literally the drawing here, right? There are so one coefficient was 2, so 0, 1, and 2. One coefficient was 1, so 0 and 1. So there's 3 chances, 2 chances. So it's the 3 by 2 rectangle like this, which is exactly what it is. It's a 3 by 2, I mean, parallelogram. Yeah. So S is finite. And the final step is that the set of weights, any weight space of the Varma module, remember, it's H semi-simple with finite dimensional weight space. We in fact know that the dimension of the weight space here is called the constant Cartesian function and so on. But we already know that m lambda and therefore V have finite dimensional weight space. So, and each V mu is finite dimensional, and therefore this is finite dimensional. And so mu S, V mu. But this is a vector space that contains u n plus times v. So therefore here. And so R. Okay, so that's why. So it's n plus finite. Therefore, the highest rate modules have these 3 properties. So now what happens? So this was just a lemma. What was the number? C. So 2D. So now if I take V1, V, let's say K are all highest rate modules. We know that a single highest rate module had these 3 properties. So now what can we say about this? Each of them was singly generated. Sorry, if these guys are highest, then V1 plus Vk. What can you say about this module? So first of all, it's not singly generated, but it is finitely generated. Second, it is H semi-simple because each of the modules is H semi-simple, so the direct sum is. And with finite dimensional weight spaces. And the third digit is n plus finite. Why is it n plus finite? Because if you take any vector in the sum, then you can write it as a direct sum of some vector here to some vector here. When you apply un plus applied to each individual component is finite dimensional. So un plus, so the direct sum of those spaces is finite dimensional, and un plus applied to just the sum directly is contained in that finite dimensional subspace, so it's finite. So this is what happens. Okay, so therefore a direct sum of finite direct sum of highest rate modules satisfies these three properties. And now we are going to just, so the goal of this master class or series of lectures is to discuss all the modules that satisfy these three properties. That set or class of modules is called the category O. So define, definition. Now with this we can finally come to the definition. It's not yet halfway, so I'm glad that before 25% of the lectures were done, I got to the definition. So 3. This means so. So sometimes people call it the BGG category, because this BGG is the name of the 3 authors who wrote the paper where they defined this category. There are 2 Gelfands, and one of them actually is the son of the other. And there's a Bernstein who was a student of the father as well. Category O, over a semi-simple flow, over a complex semi-simple algebra. G. Yeah. As as objects. So remember that the category consists of objects and morphisms. In fact, I've even told my linear algebra students about that. At least one of them is here, maybe 2. Okay, so as objects, all G modules. Maybe I'll just give these names. I don't want to keep writing this again and again. So let me erase the finite dimensional part because you can prove it. It's semi-simple. Let's call this O1, O2, and O3. Okay, so O1, O2, O3. So satisfying O1, all the objects. That is the definition of the category O. These 3 very short to write properties. Finitely generated, I mean, as a module, right? So I don't need to point that out. Okay, great. So, fine. Do I want to immediately give you examples? Oh, sorry. What is remaining? Yeah. Morphisms. And morphisms are just all G modules. When one says that morphisms are all G module maps, this is also just called a full subcategory. That's just an abbreviation for saying that the morphisms in the smaller category are all the morphisms in the bigger category. So this is a category, this is a subcategory, it's a full subcategory. Okay, fine. So that is that. Okay, great. So examples, I suppose. So Varma modules, highest rate modules, and as we said, finite direct sums of these. So maybe this is some basic examples. More generally, let us look at some operations under which O is closed. Yeah, why not? So, if you have finitely, if suppose each of these modules was not a highest rate module, but was a module in category A, then each of these is finally generated. So the direct sum is still finally generated. If each of these is H semi-simple, then the direct sum is H semi-simple. Because it is, what does H semi-simple mean? There's an eigenbasis. There's a basis of each of these guys, which is simultaneously eigenvectors for all of H. But then you take the union of those bases, and that's what coproducts do. This is a coproduct, and the union, the coproduct of the bases is the basis for the coproduct, again as linear algebra. This is a linear algebra fact. And each of those being eigenvectors for all of H, the union is still another such basis. So this, and n plus finite again for the same reason. If each of these is n plus finite, then you take a vector in the direct sum, and the same logic is. So this part, so maybe I should call this part as one bullet point, m lambda natural modules. This is the second bullet point, that is finite sums are still in O. So I should maybe put those bullet points under each other. O is closed under finite direct sums. That is why finite direct sums of highest rate modules are there, because highest rate modules are there. And the second problem. Similarly, if I take just take one object in O, finitely generated, and I take any quotient of that object, that is still finitely generated. The generators go to generators. Maybe some of them become zero, but they still are generators. If it's semi-simple, the quotient is semi-simple. Check if you don't believe me. And if it's n plus finite, the quotient is n plus finite. So O is closed under quotient. So in fact, I can even remove highest rate modules from here, because if one more modules are there, then highest rate modules. So really, these are really the sort of basic building blocks of category. Okay. But there are, so now this doesn't answer some other questions. So for example, what about submodules? Let me just put back highest rate modules. Really, highest rate modules are the building blocks of category. What about submodules? Is O closed under submodules? So that, yeah. So there is one way to do this using some Noetherianness properties and so on. I suppose that Artinianness properties. Yeah, but because UG is Noetherian. Yes. But we will do it in a different way using what we have already seen, which is central characters. And the last point is, so there are so when I have, suppose I give you two different modules, right? So of course you can take the direct sum of those modules. If those two modules were individually in category O, then the direct sum is also in category O. But there are other ways of combining or adding up the modules. Basically, think about short exact sequences. Okay? So if I know that I have a short exact sequence of G modules and the outer two modules are in O, then is the module within the central module? That's called extension. So again, another question is O extensions. As we will see, the answer to this question is yes, and answer to this question is no. So let us maybe, will you do that in the extensions? You can do the tutorial. So Teja will do the tutorial, the extensions part of the tutorial. He will give you an explicit example where the two modules outside are there and inside are not. Why does it fail? So what property can fail? So if you suppose if we think of a short exact sequence, right? Yeah, should draw. So maybe I should write down this. What can fail for? So clearly, the submodule thing works. So I'm not discussing it. But so what can fail? Maybe I should call this as part C, because the examples in part B are sort of immediate. The examples in part C are not yet done. Okay. So what can fail? For extensions. So O1 actually works, right? So okay, maybe I should say, so say 0 to M to, sorry, let me call it M prime to M double prime, usual notation for short exact sequence. So suppose we have G modules, okay? And M prime and double prime are in O. So what we just said was, so the question really is, suppose M is in O, then what do we know about M prime and M double prime? M double prime is clearly in O, and we will prove that M prime with the submodule is also in O. So maybe even sub-n extensions. Let's look at it. So first of all, submodules. So say M is in O, then M double prime is in O, that is obvious. And the question is whether M prime is in O. So what can fail here? So it's semi-simple that if you have a submodule of something that's semi-simple, then of course it's semi-simple. Take each eigenspace, each weight space separately. The weight space is the subspace of the original weight space. So take a basis of that, of the subspace weight space. N plus finite is also clear because take any vector in n prime, it is a submodule of n. So if you apply un plus to that vector, then that's the same as applying un plus in this module, which is finite dimension. So O2 and O3 are fine. It's O1 that's a question. How do I know that a submodule of a finitely generated module is finitely generated? That's where you use material and so on. Yeah. So O2, O3 are fine. Why does O1 work? Why is O1? Why is? And the answer is because UG is Noetherian, and you can do that also. Teja will do UG the Noetherianness. So, but as I said, I will prove it using a different way, using central characters, because that approach yields many other things. So I just want to do one thing. Similarly, so second is quotients. So second is extensions. So if the middle guy is in category O, then we will prove that both the side guys are. The question is, if the side guys are in category O, then is it true that the middle guy is? And the answer is no. What can fail? Is M in O? Okay, so if okay, so let's see. Suppose M double prime and M prime are finitely generated, right? Then you can check that M is finitely generated. That's not hard to check. Right? Basically, lift some generators from here to M, take these generators, and that union is the full. Check. Maybe that's a nice question to check. Check that O1 holds. And O3 holds. Here O2 and O3 are easy. This check is actually a question too. Right? The same thing. So finite generation is because you lift some generators here and here. Here. O3 holds because if I take any module, any vector in M, right? First subject it onto take the image of the vector here. Now un plus here. Let's see, is that true? So un plus. So if I apply the object here, or I can just look at weights, is it? For this, actually, the correct thing to do is to look at cones of weights and so on. So I'm going to say M in N. I'm going to do un plus of this. Apply to M. So first of all, let's say this subject on the M double prime. So un plus M double prime, right? This is finite dimensional. But that means exactly that means that this mod M prime is finite dimensional. Now, how do you prove that this is finite? So you have to take the pre-image and maybe look at cones or something. I don't know. Anyway, but already, maybe I should ask the question. Does O3 work? O1 does. The point that definitely fails is what the H semi-simplicity part fails. Okay. Check whether O3 works or not. I think it does, but one has to write this down. Okay, so extensions may not work, but now let us go towards why submodules work. Okay, maybe I should not have erased that because I haven't finished this board. So I gave you some examples. This was CMN. PC. Okay, so let me do 3D. So now let me do another example. That is neither a direct sum of Verma modules or highest rate modules or not a Verma module. Okay. Let's look at this example. That's a interesting example, and that again will be useful in what we do later after the central calculus. Yeah. So here is an example. So let's say this is say G is SL2. Just for simplicity. The example makes sense over any semicircular algebra, but let's do SL2. So okay, and M or question. M is so remember what the Verma module was. First, let me write down the definition of the Verma module. This was the Verma module. Now I'm going to change it slightly. I'm going to quotient by E square, not by E. So now the image of 1 is not killed by E. So it is not a maximal vector. Okay? The claim is that N belongs to. So proof. Let's check this. Okay? So first of all, M is again still it's a quotient of UG. Therefore, so M is the same as UG times the image of 1, whatever this vector. So it's singly so finally generated. Okay, great. What can you say about the structure of M itself? So what? Okay, let's write down some basis, right? So again, let's do the same like PVW kind of property. You have UG and V squared, right? So let's write down the complement of U. So UG, remember G is SL2. Equals, so okay, so I want to get rid of this part. So let's see. So it's I want to write down the complement, right? So UG can be squared. Right. What is remaining? What is the complement of UG times E squared? That's maybe what I should ask. Under again, same. Let me write this down just so you know. This is UN minus. This is U H. This is U plus. So what remains after I take out the E squared part?
If you pick an ordering where the E comes last,
Yeah, F, H,
then
yeah.
then what remains is 1E and no E's.
1E and no E's. That Raghuram? Yes, it is. I see the voice. Okay. So okay. So UG times yeah. So let's write this down. So UG times E. Sorry, not UG. So what should I write down? Tell me something precise. 1E and no E. So what else should I? So I have to
F and
just ignore because this part is what changes. The other parts I should leave. So I should be writing down, let's say U. Well, let's say CF. Tensor CH. This is the tensor CE, CE, 1E and then no E's. That's it. But now again, out of that, I want to get rid of this part as well. This part certainly comes out of here. Once it comes out of here, I can get rid of and it comes out of both of these places, I guess. So now let me just write this down. So this is something one has to check. I mean, let me write down the two parts one doesn't have to check, and then the part one does. So UG times E square. This was already there. Direct sum. Let me write the third row first because that is easier to check. So this is because I'm subtracting, I'm taking away a maximal ideal, the ideal generated by this one linear term from this algebra. So certainly UG times this contains whatever here. So CH times the maximal ideal times CH. So what remains behind is the complement, which is just scalar stuff. So I can remove this tensor C. Now, now here is where one has to check. This part one has to check. I want to take away the maximal ideal from here. I can do so. I will leave C only, but then of course there is something about how can I take it from the middle when it was at the end. So for that you have to also observe the commutation relation H bracket E equals twice C. But you can do that, and so what you would get here is CF tensor. Oh, sorry, I forgot to take away the thing. So plus UG H minus lambda of H. So this part that I'm quotienting by plus these two things. Okay. And you can now check that basically these guys applied to the image of one are exactly the what. So by the PBW theorem, when you quotient this entire UG, USL2 by this, you get exactly this much remaining. That's fine. And you can check that verify that H applied to any of these guys is perfectly fine. So let me say that now. So M is isomorphic to this last part. So CF tensor E. So E times 1 bar and 1 bar. And you can check that the weight vectors and we check. So if you apply H to let's say F power K times E times 1 bar, then you get any guesses? It's going to be easy to guess. Right? When you apply H to 1 bar, you get lambda. So when you apply H to E times 1 bar, you get lambda plus alpha, or lambda plus 2 if you want. And then when you apply F power K, you get lambda plus 1 minus K times alpha. That's 1 times. So this is the extra scaling. So it is indeed an eigenvector, you can check. And similarly, H times, what was it, F power K. This is similar, it's lambda minus K times alpha. Oops, lambda minus K alpha H. Okay, great. So indeed, it is these guys form a base. The two terms mentioned here form an eigenbasis or H. So indeed, O2 is satisfied. It's semi-simple and what are the eigenspaces? Actually, I did not need the finite dimensional weight spaces as the defining axiom. So this is it. So O2 holds. And finally, we just check the weights for O3. Note that let me 3D. So let's see. This is this, and the third bullet point is O1, 2, 3. The weight. Before doing the O3, let's check what the weight set of this module M is. Right, the weight set of the module is basically these are the basis vectors, so the weights are exactly these. So it's lambda minus K alpha, or K going from 0 to infinity and plus 1 minus k alpha. So you'll be subtracting. So k goes from here from. So anyways, I'll just say lambda minus k alpha where k is in. So this lambda itself is a weight from here, f power 0. And the lambda minus alpha, lambda minus 2 alpha. Oh, e is also weight. Sorry. So what should I do then? Lambda plus alpha minus. That. Okay. So now clearly, if I take any weight vector of some weight and I apply the raising operator as many times as I want, I can only go through finitely many weights. We saw this thing earlier. I'm not writing this out again. It can only go through finitely many weights. Each weight space is finite dimensional by the previous part. And maybe I'll say that here. In fact, you can check that each weight space is dimension 2 with one exception. Except the dimension of m lambda plus alpha. That is just the point that e times 1 is a weight vector which of the weight lambda plus alpha. It doesn't go here, it only goes. Every other weight occurs with dimension. So if you're going through finitely many
This
weights,
is equivalent to O3.
sorry again.
This is equivalent to O3, right? At least given O1 and O2 as a background assumption.
You mean these two properties are equivalent to this and this? What is it?
No, the weights. So the weights being bounded above, or for every weight you can only go up by a positive root finitely many.
That's right. So the weights are bounded above, so you can only cover finite many weights, and each weight space is finite dimension, and that's that's O3. So okay, great. So I mean, I'm not writing down the equivalence, but yeah, start with a weight vector, start with a vector, break it down into weight vectors, apply the n plus to each of them. So the thing that we already saw, I'm not repeating. Okay, so this is another example of a module which isn't a traditional Varma module, high strip module, direct, hasn't been covered before, but it also belongs to category. And obviously, I could have replaced e square here by e power e. That would just give me a bunch of, I could maybe power n, and that would still give me a category O. Okay, so we are calling 3e. No, let me show. I can do that. E power l. Let's call it mn. Isn't category. Proof simple. But now let me generalize this to any semi-simple real. Again, those objects are going to be necessary anyway. So when we talk about projective modules. So now G is any semi-simple algebra. And I can do the following. Okay. I do the following. I take lambda, of course, lambda equals star. And I fix let L be some integer, not with the delta. It's not a weight, it's an integer. Okay. Then consider the module and define. Let's see if I can do this. ML to be it's generated by one vector. So this is certainly finitely generated. It's going to be killed by what is so EL is for me. How am I going to generalize EL? The rest of it I will keep the same. Summation UG. Now it's the Cartan subalgebra is larger dimension I HI minus lambda of HI. So that part I still quotient by. What do I do here? I need a little more space. Okay, so how do I generalize e power n, e or e square? The idea is the following: e square, e square occurs inside here. So my n plus was C. If I quotient by E square or the ideal generated by E square, I'm giving off all the all the root spaces all the weight spaces of UN plus of height 2 and above. If I do E, then I'm giving off the height 1 and above. So what I do here is direct sum, so UG of course, left submodule, times the direct sum of height beta equals L. UN plus so this is one subspace I kill by, and this is another. One submodule I kill by. Left submodule, and yeah. I kill things of height beta. The moment I kill things of height beta, I kill things of height bigger than beta because there's a UG start before. The same thing as. And the point is exactly the same. Once you measure things by height, if I take any vector inside there and I start applying racing operators beyond height, beyond height L, they will land, the output vector will land inside here, and so it gets killed. So you only look at height L or less, and now each weight space here is finite dimensional, and therefore in UG the weight spaces are not finite dimensional because you can cancel out n plus n minus and get or you can just get a huge amount of UH. That's actually the point. But if you just stick to UN plus or UN minus, then every weight space is finite dimensional. You can check this. And well, this is the constant partition function. We don't need to check it. We checked it last time. So therefore this, and the claim now is this is the similar claim. This claim here ML belongs to O because that was what ML was. Change. And here similarly the same thing. ML. BGG had a slightly different construction of this. They quotiented not by the height bigger than that. We could also do, instead of that, we could just do UG times n plus power L or something. That is what I think BGG did in there. But it's roughly the same idea. This is actually smaller than this because this is quotienting by everything of height L. What is it? Maybe it's the same. Fine. You can do the same thing. Check, is this the same? Anyway, so the point is these modules are again going to be very important when we construct projective modules. So we are writing down some nice objects without proving much about them, but they will show up later in the code. Okay, so now let's get to some basic properties of weight. We did not assume it, but one can prove it. Hopefully, so hopefully I can prove it. It certainly is true. Okay, we'll wait. So that is that. So we have now constructed this general object, which is this is supposed to be UG. Okay, O is closed under finite division quotients. Let's start with this was 3, so let's start with 4. We already said that it's closed under finite direct sums and quotients. The submodule part we will get to hopefully tomorrow. Let's start with every object has a every object the weights of every all n now. The weights of n are contained in the finite union. I'll write it in words. Of cones, I guess, for lack of a better word. The thing that was the convex sum of our which is lambda I minus. This is lambda I, and then we subtract alpha 1 and alpha 2 and alpha 3. That kind of cones. Okay, let's write down the proof of this. this takes me back to my PhD days at the University of Chicago, because this was literally the first paper that my PhD advisor gave me to read. And if you follow the old Russian style, somebody said told me that paper was apparently very expensive or something. So they would write very short articles. They would not give proofs. And so this has virtually, all these basic things that have no proofs. So I had to prove stuff for myself. Work it out. I think that it's a good experience, right? Once you prove, get your hands dirty, then you actually learn the math. So I learned this is math I learned 20 years ago. So we will see. Okay, so finite union of codes. So let's take some object M. So first of all, because it's a category O, M is finitely generated. Say M is generated by M1 and Mk. So some vectors. Now, what we did last time in the tutorial says that even if these guys are not weight vectors, remember M is H semi-simple. So M is H semi-simple, so therefore these guys are sums of components in different weight spaces. By applying different elements of H, we can separate out the individual components like the Bantam model. So therefore, without loss of generality, I can now separate each of these guys into weight vectors. So WLOG, I can assume that these are all weight vectors themselves. Just take the updated list and call that M1, M2, M3. So M is generated by these guys. Each one separates or splits. So M is generated by all of those guys. So call those guys itself as M1. WLOG, Mj belongs to Mj for all J. And I'm not saying that the mujes are distinct. The mujes can be equal. But then if the mujes were equal, I would just combine them. So let's take the mujes. Combine all the MJs in the same weight space together. Oh, no. Maybe the generating action is different. I was right. Fine. Okay. So fine. There are some weight vectors. Mujes, of course, are in. Now we don't know anything about category O can have objects of any highest weight. So mujes are in H star. There is no connection to some lambda minus some of all. Fine. What do you want to prove? So, continue. Now we have again this category O. So we are going to use all the axioms. So we've already used O1 and O2. Now we use O3. Right? So we want to talk about the weights of M. But now what is M? M is so let me say so M equals summation G times Mj. Again, by the PBW isomorphism, Ug is Un minus UH Un plus. Un minus UH. By the way, I could have done PBW theorem in a different way. I could do Un minus, Un plus, and UH. So let me do that instead. Because PBW theorem doesn't care about right? So now what is UH times Mj? Mj was a weight vector. So no matter how I act, I just rescale by some scalars. So let me just say, maybe here I'll say PBW. Mj PBW. Yeah, okay. So now I have set PBW theorem here. Yeah. Now this part is just the same as the span of M. Maybe people can't see it on the screen. Fine. This part is just Mj because it's a weight. So now we get Un minus Un plus times M. And now we use the property O3. Un plus Mj is a finite dimensional vector space. It's finite dimensional. It's a finite dimensional subspace of M. which is H semi-simple. M is H semi-simple. Here is a finite dimensional subspace. So take a basis of this subspace if you want. Actually, you can take a spanning set from here itself, right? This is a spanning set of monomers spanned by levers in n plus. So take such a spanning set. Each of them is a eigenvector or root vector or something for add of all of H. Therefore, that times Mj is still eigenvector, right? The same thing. Un plus times some beta times Mj contained in n mu plus Uj. Right. So again, therefore you have a basis, you have a spanning set of this set consisting of weight vectors. Say Un plus Mj is spanned by let's give this Mj1, Mj, let's say Kj. And each of these guys has its own weight. Of H weights. Let's call this mu J1, mu J, Kj, respectively. So Mj1 has this weight, Mj Kj has this. Is that clear? All I'm saying is that you apply UN plus by O3, this is finite dimensional, but also UN plus is spanned by you have to be, of course, spanned by all the possible words in some PBW basis. So those infinitely many words span a finite dimensional set. Therefore, by basic linear algebra, there's a finite spanning subset. In fact, a basis, but fine. So take a finite spanning subset or a basis of this guy. That is some lever times Mj. Therefore, you get these guys which are themselves weight vectors. And so they have some weights. And now what do I do? So therefore, so now let's go back to the original. M, the original module, is summation j goes from 1 to where k. Oh, maybe I should call not these, let me not call this kj, let me call this lj. And now for each j, I sum from R goes from 1, I need a letter, lj. Un plus mj is done, so un minus. So now what can you say about the weights? Now the weights of this guy alone is how much the weights of this guy are exactly the weight of this guy, and then you subtract positive roots. It is precisely the weight of this guy, which is mu j r minus, sorry, every weight of this guy is of the form mu j, and then you subtract some positive roots. So these weights are contained in mu j r minus this. That's for all r and for all j less equals k and r less equals n. But if that is true, then when you take the sum of these subspaces, then the eigenvalues of a sum of vector spaces are contained in the union of the eigenvalues. So therefore, if M is contained in the union, J goes from 1 to R, so 1 to A union. Now R goes from 1 to Lj. This is exactly what we wanted to do. Okay, we have 5 minutes. Okay, so one writes it out, but you see, we had to use both O1 and O2 and then O3. So this was where we used O2. This was where we used O1. Finite generation, H semi-simple, and the tutorial, and then O3 is this. Okay, fine.
Can I ask a question?
Yes, you can.
So can we take this the finite generating set over UN minus to consist of highest weight vectors?
There is always okay. Can we take the finite generating set to consist of highest weight vector? Here is the answer. The answer is no. So that's a nice question to end. Until the next one. Huh? Exactly.
One more story you can finish it has like
I will do next time probably. Let's see. Let's write down the question. Can the generators O1 be taken to the highest weight? Highest weight vectors first. I think I'm using the word maximum vectors. Right? And the answer is no. For example, the modules we already just looked at. M2, which is UG, USL, even for SL2, mod E square and H minus lambda. Here, the point is it is generated by one vector. But what do you know about one vector? E times the one vector is not 0, but E square times the one vector. And so actually, let me write this down. So I wrote down this vector last time. I wrote down the module, but what I didn't write down was E square times 1 bar is 0. Therefore, I have a submodule, which is UN minus 10 E square, is a submodule of M, M2. I call it ML, and here L equals 2, so M2. Okay. And what is this? The E square now is the highest weight vector. Sorry, God, E power 1. Right? And now this is E times 1 is a maximal vector because E square times E times that is E square times 1. That is 0. So E times 1 is a maximal vector. What is the weight of this guy? It's this head weight lambda. It's lambda plus 2 or lambda plus alpha. So this guy is actually isomorphic to CF, which is we saw the basis of this. This is exactly the Varma module of weight lambda plus alpha. And now, so I have a module, I have a submodule. So of course I have a quotient module. So we have, this is the submodule, which is just E times UG times E times 1. Now we have M2. What is the quotient module? What remains after I take out E times 1? And all the vectors Fk times E times 1, if you look at the notes, Fk times E times 1 bar was one set of vectors. And the remaining set of vectors was Fk times 1 bar, F power k times 1 bar. Now, 1 bar is not maximal, as you said, because E times 1 bar is not 0. But when I look at the quotient, E times 1 bar occurs inside the quotient. So E times 1 bar is 0 when you look at M2 mod this guy. That means 1 bar generates a maximal vector in the quotient of these guys. And that is the series for, that's a short exact sequence that describes the module that I have discussed. And that is the story in general. You will find that every object in category O has some submodule and quotient. You can write down, now in this case, it was nice that it had a 2-term short exact sequence in Varmas. In general, it will have multiple terms, but the nice thing is every one of these sub-quotients is going to be not necessarily a Varma module, but certainly a highest weight module. So in some sense, that's why I said every object in category O has a finite flag, if you will, finite chain of submodules, so that successive quotients are highest weight modules. And that is why highest weight modules are the building blocks of category. Okay, so we will start next time with this, with some more basic properties like this.
those are all maximal vectors, then our model is directional.
Right. So if these are all my highest weight vectors, then you would get direct sums and so on. But let's not. Well, you could quotient out the direct sum by some common factor. M0 plus M0 quotiented by the diagonal or something. Maybe, I don't know. Anyway, but yeah, the point is just like this happens even for modules which are not highest Varma modules or highest weight modules, but slightly more complicated, E2. Similarly, you can do the same kind of thing now. I can do this for EL, e power L, and check that at each step you get a finite chain. And actually, maybe I'll write this down and we should stop. 32. Now, let me give you 1 minute to write this down. And I'll just say that the substitutes of quotient, because this is the correct time to say more generally. Sorry. Want to do too many things. With ML is above, with G equals SL2, and ML is above, we have defined that module. We see that 1 bar, E times 1 bar is not 0, but E power L times 1 bar is 0. So I get, so we get a, let's see, M equals ML, contains the module which is generated by UG times, what was it here? It was UG times E1 bar. So I can get UG times E1 bar, contains UG times E square 1 bar, contains UG times E power L minus 1 times 1 bar, contains 0. And the subquotients are quotient is what it is precisely. Okay, here the quotient I know. This is the quotient is the Varma module of size lambda minus L minus 1. So here the quotient is lambda minus 0. Here the quotient is lambda minus alpha. And so on and so on. Every time you get a quotient, here the quotient is M lambda minus L minus 2 times alpha. M lambda minus 2 alpha. So in general, this module has not just a short exact sequence, but a longer chain of submodules. And the successive subquotients are exactly Varma modules of different lambda minus alpha. Oh, good. Something is very wrong. No. It's the other way around, right? There should be pluses. Plus, and plus. Now that's correct. The terms were correct. I missed a sign. Right? But so yeah, you see that the chain of submodules and the subquotients are exactly of the same kind. Lambda at the top, then you keep increasing, adding an alpha as you go. And that is what happens in general for category. Okay, we should stop.